And here I want to show you how to find the indefinite integral by recognizing the use of the natural log function within that integral. We already know a lot of rules about integrating. For instance, we know the power rule. If we're going to take the integral of x to the n, we raise the power by 1 and then divide the coefficient by that new power. We know about the natural log, that the integral of 1 over x is the natural log of x, and the integral of e to the x is e to the x, as well as a couple of trig functions as well, like the integral of cosine being sine and the integral of sine being negative cosine. What I want to do is think about the integral of 1 over u du. We know that that integral is going to be the natural log of u plus c, but what if u is a function of x, so like f of x? Then du is going to be f prime of x dx. And what that means for us is that we can rewrite this integral as being the integral of 1 over u, which was f of x, du, which is f prime of x dx. Or if we clean that up, it would be f prime of x over f of x dx is going to be equal to the natural log of u, which we said was f of x, plus c. And what we have here is what we call the natural log rule. So this is what we're going to want to look for today is anytime that we are trying to take the integral of a fraction where the numerator is the derivative of the denominator, then that integral is going to be the natural log of whatever is in the denominator. Let me show you what I mean. If we want to find the indefinite integral of secant squared of x over tangent of x dx, what we recognize is that if my denominator is a function, tangent of x, and its derivative then is going to be secant squared. So we recognize that our numerator is the derivative of the denominator, and that means that we get to jump straight to the answer being natural log of our denominator, natural log of the tangent of x. Here we have the integral of 2x minus 3 over x squared minus 3x plus 4. So with our denominator being x squared minus 3x plus 4, its derivative is 2x minus 3, which is exactly what our numerator is. So we have the integral of f prime of x over f of x, so we can jump straight to our answer being natural log of the denominator, x squared minus 3x plus 4. And of course, plus c. Sometimes it doesn't work out exactly as planned, but recognizing that there is some natural log rule happening can help us with some guessing and checking. For instance, here when we have the integral of 1 over 2x dx, well, if I have my function, my f of x being the 2x, its derivative is just 2, right, which is not exactly what we need. In my numerator, I don't have a 2, I have a 1. So from this, 1 would just be half of that derivative, right? So how does this play out in terms of the natural log rule? Well, we have f of x in our denominator, but our numerator being 1 is not the derivative of that. It's half of the derivative of that. Now, earlier we saw that the integral of half of something is the same as half of the integral of that something. So if we have half of the integral of f prime of x over f of x dx, then that is going to end up being 1/2 of the natural log of our denominator, which was 2x. So if we have the integral of 1 over 4x minus 1 dx, we think about f of x being our denominator, 4x minus 1. Check out its derivative, which would be just 4. That is not what our numerator is. Our numerator is 1, which would be 1/4 of that f prime. So our answer is going to be 1/4 of the natural log of our denominator. Let's kind of stretch ourselves a little bit here. If we want to find the exact area of the region bound by the x-axis and the function f of x equals x over x squared plus 1 on the interval from 0 to 3. Well, we're going to have to remember that area, the exact area, is the integral, but the definite integral from 0 to 3 of x over x squared plus 1. Now we recognize that if f of x is our denominator, x squared plus 1, the derivative of that would be 2x, which is not our numerator. Our numerator is only 1x. So if we wanted 1x, that would be half of f prime. So our exact area is going to be half of that integral from 0 to 3 of f prime over f, or 1/2 of the natural log of our denominator, x squared plus 1, evaluated from 0 to 3. Now the extra step, of course, is to do this evaluation, and we start by plugging in 3 first. So natural log of 3 squared plus 1, that's 10, minus natural log of 0 squared plus 1, which is 1, and natural log of 10 exactly is natural log of 10, but natural log of 1 is 0, so half of that is just going to be 0. And our exact area would be 1/2 natural log of 10 minus 0, or just 1/2 natural log of 10. This last one looks very similar to the last ones we've been doing, but if we let f of x be that denominator, then we have a product rule. And so the numerator would be 1 d2 plus 2 d1, which would be 1 plus natural log of x, which is not our numerator. So let's try a different approach. We still have all of our other rules and stuff, so let's use that change of variable method where we let u be just the inside of that function. I'm gonna be very deliberate about this, and I'm gonna let my u be the natural log of x. Then du would be 1 over x dx. We can go back to our integral here and rearrange this. Because I have 1 over x times the natural log of x, that's the same as 1 over natural log of x times 1 over x dx. And using our u substitution, then, we would have 1 over u, and 1 over x dx is du. And we already know that the integral of 1 over u du is natural log of u, or since u is natural log of x, we'll have natural log of x. I want to point out one little thing here. Going back to that original integral of 1 over x natural log of x, it's all about how you rearrange the function, and that because I'm multiplying the denominator by x, that natural log by x, what I can do is rearrange that and look at it as being 1 over x over the natural log of x. Then we see that if my denominator, natural log of x, is f of x, the numerator now is that derivative, f prime. So we are using the natural log rule. It would just be the natural log of our denominator, which is another natural log.